transmitting, right? In 100 bit, you notice you already collide with someone else in CSMA. You still keep transmitting the remaining 9,900 bits. But that transmission of 9,900 bits basically is useless because your transmission is already collided, right? So, of course, here that if you know that at the 100 bit, you are already colliding with someone else, what's the point for you to transmit that remaining 9,900 bits? There's no point to keep transmitting that remaining 9,900 bits, isn't it? So that is here, that implement for the CSMA is. If you know you are colliding with someone else, don't transmit the remaining bits. Because the transmit of the remaining bit is just a waste of time. So that is here, CSMACD. But now, of course, you say, how can you know you are colliding? You are colliding with someone else, right? So after you have started your transmission, you keep monitoring for collision. If the collision is detected, abandon your current transmission, choose a backup, and then abandon your current transmission, and then try again later, right? That is CSMACD. Okay. After you have started your transmission, keep an eye for collision. If collision is detected, abandon the current transmission and try later. Okay, so that is it. Of course, how much time you need to detect the collision? But obvious. After you have started your transmission, you just need to monitor 2T Pro. Okay, that round-trip delay. After the round-trip delay, if no collision detected, you should know that your transmission should be successful, right? You just need 2T Pro to detect the collision. Okay. So that CSMACD, the performance can still be mathematically analyzed, evaluated. Okay. This is just showing you the model. We don't go to the details of those. Just to show you the result. CSMACD throughput. That is here. Okay. Okay, that is the throughput. Maximum throughput. That is here. Okay. Quite obvious to show you. So that for the Ethernet, actually, that medium access control we are using is CSMACD. Okay. This is an application of the CSMACD. We use the one persistent CSMA, and if the data rate is 10 megabit per second, the T-Pro, 2T Pro round-trip delay, we say limited to 51.2 microseconds. Then you will see that for that 51.2 microseconds, how many bits can you transmit? You can transmit only 512 bits. That's 64 bytes. Okay, so that is here. For Ethernet, we actually specify that the frame should be at least 64 bytes long. What's that minimum frame size is 64 bytes long. Why we put that constraint? That is, we want to know that if one frame is colliding with someone else, you should know your frame is collided. Okay? So if you say, remember that in maximum you may need time 51.2 microseconds to detect the collision. If your transmission time, your frame transmission time is less than 51.2 microseconds, say you only need 20 microseconds for your transmission. And you're actually colliding with someone else at 30 microseconds. Before that collision is detected by you, you already finished your transmission. So you may assume your transmission is successful, but actually it's not. You are colliding with someone else. So that is here. We say in an Ethernet, we say we don't actually use acknowledgement. We use the collision detection to assume if your transmission is successful or not. If you say you finish your transmission and no collision detected, you assume it's successful. Then you finish it. Okay? Only when collision is detected, you may try again. Okay? So that is here. 51, we say the frame size, minimum frame size, 64 bytes. Okay? So another specification for Ethernet is how to do the back off. We say Ethernet, for the CSMA CD, we say collision detected. We choose a back off, then you try again. How do you do the back off? We use the truncated bounded exponential back off. That is here. For the nth collision, we select a random back off, random time from 0, 1 to 2 to the power k minus 1. K is minimum 10, 10, n to 10, right? Choose a random number, then back off. Then say you choose a random number, say R, and then times 51.2 microsecond. Okay, so that is the delay back off time. Then how many mini slots you need to back off. Okay, so that's comparing the performance. Of course, you will find that CSMA CD is much better than other CSMA schemes, of course. But again, depending on normalized delay bandwidth product, you will find that if the normalized delay bandwidth product is quite big, Aloha can actually perform even better than CSMA. Okay, so that is about the medium access control. We will stop our lecture here. The remaining slides will be covered next week.
We can do it, boys. We can do it. The main point is just like learning.
For area networks, so I explain to you the medium access control mechanisms they already have in this industry, right? The second part of this lecture, I explain how those mechanisms are applied to the real system. We focus on the LAN application. The medium access control is mainly used in two scenarios. One is in a radio communication or wireless communication. Okay, the other one is actually about the LAN, as all the users share a cable. So here we focus on the application of medium access control in a LAN scenario. So what is a LAN? LAN first is referring to such a system which is owned by a single entity. Usually it's a private ownership, right? Like a company network or COD network is owned by COD network. Okay. Another feature of the LAN is that it's geographically limited. The distance between two users is actually quite limited. Usually we say within 1 kilometers, right? So because the distance between two users are relatively short, so we think the channel quality is relatively good. So we don't need to worry too much about error recovery. Right? Usually we say we only detect the errors, but we don't usually try to recover from the errors. Okay? So because we don't really need to do the error recovery, so the system is relatively easy, simple. And the third feature about the LAN is another one. Usually the users may actually move around inside the network. So it's a bit difficult if you try to track those users moving around. So that is here we say, because you don't really know where the user is, you just broadcast over the whole network. No matter where the user is, even if it's still within this network, you will receive the message. So that is here for LAN. Usually we say we use the broadcast mechanism. Okay, but one feature of the broadcast network is that we need the medium access control. So that is here. A typical LAN, you will see that they share a cable. Everybody is attached to the cable, right? So how to actually attach to the cable? That usually is we have one particular hardware, or we may call it a firmware. We call it network interface card. That is this one. Network interface card attached to that to your any device. Then another side connected to the cable, right? So medium access control actually in a protocol stack, it belongs to data link layer. So data link layer actually has two sub layers. One is called medium access control. That is here. Then it's the interfacing to the physical layer, right? And another one is called logical link control. Now for the logical link control, usually we may have some protocols, as I mentioned to you in the last lecture about HDLC or point-to-point protocol. Okay, for the Mac, of course, we say you can have Aloha, you can have CSMA, CSMCD, CSMCD, LD.3, and so on, right? The whole actually is called data link layer. So coming to the service provided by the data link layer. They may have three types of services provided by the data link layer. One is called unacknowledged connection service. That is, you just try your best to deliver the message, but we don't guarantee the message will actually be successfully delivered or be delivered error-free. We don't even let you know if it is successfully delivered or not. It's called unacknowledged.
Oh, hey, man.
If that is the service provided by the data link layer, then
it is. Oh, this guy's got a
provided by the Mac, then that is here for logical link control.
that thing.
Actually, it's empty. So we don't really need.
We be trying our best to
Another type of service provided by the data link is called reliable connection oriented service.
Hey, me down site manual. No, not really actually. That's actually not true.
For the logical link control, you may have to implement ARQ like HDLC, right? And the third one is
because I mean that doesn't work for me. Like that's what I'm basically just saying.
If it is successfully delivered, we will let you know. So that is here. We need positive acknowledgement. Then you also need logical link control to actually send acknowledgement back. Okay. So that is showing you that what is the role played by the logical link control. Of course, another role played by the logical link control is actually that multiplexing. If you need multiple connections over the data link layer. So that is here, logical link control. We have one particular field is called
manual is good if you're trying to snipe, but not for normal stuff.
Telling you what's the destination service access point, what's the source access point. We can have multiple connections over a single data link layer, right? So this is showing you about encapsulation from the network layer. We may have an RP packet, then LLC header will be added to provide logical link control services, then MAC header and tail to provide MAC services, right? So coming to the Ethernet itself, it was developed in 1970s initially. The Aloha net, right? I explained to you Aloha. That is the first of the LAN. Then in 1973, McAfee proposed the Ethernet concept. That is the structure of the Ethernet, right? Initially proposed then. So coming to the Ethernet, the medium access control used is actually CSMA-CD. And the CSMA...
Right, we're not going to win this match, no. But like...
You may still remember the one persistent CSMA? You sense the medium.
No. I'm going to win this match. That's the aim setting is fine.
However, if you find that the medium is busy, you keep monitoring.
I've been playing this game for a while now.
Then you transmit immediately, right? Okay, after you have started your transmission, you keep monitoring for the collision detection. That is called CD, collision detection. If you find the collision actually occurred, you abort your current transmission, and then you try to take back off.
Enemy Goliath.
Again. So that is collision detection CD, right? So now, of course, we say how long we need to detect the collision. In maximum, you need a round trip delay. That is the longest distance up to any users. That's user A and user B. User A started transmission, and then
from this side.
To user B, and then coming back to user A. That's round trip time, right? You need that round trip time in maximum to detect that collision. That round trip time in Ethernet is called a slot. That is called a slot. So that is a very important concept in Ethernet. Slot. Okay? That's actually the time for you to.
I think just the sites, just no, whatever.
Right? And also, when we choose backoff, we also say we always backoff a multiple number of slots. Okay, so that slot is very important. And also, because that slot is the time for you to detect a
Your boy,
collision.
Chica.
So we also have the requirement for Ethernet is your transmission time cannot be.
I just didn't want to use the minigun, to be honest. Like just in that literal that match. Yeah, that was the only reason. I should probably try the other operator skills, but yeah.
We have a requirement that the frame size, your frame cannot be too short.
Because like everything was a bit tight there, so.
Frame size requirement. So that is the slot also specifies the minimum frame size. Okay, the backoff, let's say the truncated bounded exponential backoff. That is for the retransmission, and you choose a number between 0 and 2 to
yeah, it was just sometimes it happens, man.
You back off R times slots. That is, and also we say we call it a truncated. That is because you will see that K cannot be greater than 10. And also, we say for Ethernet we only provide the best effort service. That's because if you already tried 16 times, still unsuccessful, we simply give up the try. Okay. So now coming back to the slot, and also the minimum frame size. Ethernet was initially proposed. The data rate was 10 megabit per second. Okay, and the round trip time is 51.2 microseconds. So that is 51.2 microseconds. The distance.
Oh, there's a bit of a lag there, but.
Yes, one way is 10.24 kilometers. If it's a round trip, right, that's 5.12 kilometers. That is saying for Ethernet and megabit Ethernet, the maximum distance.
Come from? Yeah, literally that guy.
But usually we don't even go to that far, right? So now, for that 51.2 microseconds time slot, how many bits can we transmit if the data rate is 10 megabit per second? That is 512 bits. That's actually 64 bytes. So that is, if you look at the Ethernet specification.
If I was someone, I'd definitely be up in here.
Minimum frame size, 64 bytes. Then of course you may ask me that, if we say my frame size is not 64 bytes,
yeah, call it.
What can I do?
This came from the corner.
Your frame size is only 32, which is smaller than 64 bytes. You do some padding. Let's add some padding bytes to make it 64 bytes. When I show you the frame format,
that grenade. I need.
Padding is needed to make the frame size at least 64 bytes. So you look at the frame size, 64 bytes. You see that it's actually.
It was right next to me.
Because the round trip delay we say is 51.2 microseconds and data rate 10 megabit per second. Right? So you will find that if we say the data rate is not 10 megabit per second, it's actually 10 times faster, 100 megabit per second.
Oh, don't worry about it, man.
You will find that for that interval 1 times 51.2 microseconds, I can transmit 5,120 bits. That's
that was starkly hiding there.
40 bytes. Then you will see that. Then you will see, okay, now the minimum frame size is not 64 bytes. It can be 640 bytes. What can I do? They say, how about the specification? Do we have to change?
Did I not get the guy? What happened?
Specification for 100
the game just glitched. Oh, that paralysis thing. Yeah. Cool. Yeah. Hit by predator missile. Good job. Oh, that guy's right there. Oh.
Developed, we try to keep it unchanged. So then we say, how about 100 megabit per second? So that is here. We say if the data rate is increased 10 times, you try to keep the minimum frame size still 64 bytes per 64 bytes. What can we do?
Stealth chopper.
What can we do actually is we reduce.
Come on, move. Am I stuck again? No, we just lost.
About 10. Okay, so that distance, not 5 kilometers now. Now it's
I cannot single-handedly. Oh, might be possible, but still.
Keep the minimum frame size unchanged. Okay, so now coming to the frame format. First, you will see that that is we have the pad field. The purpose for the pad field to make sure that frame size at least 64 bytes. So that is your starting frame and start destination address to the end. Okay, at least the 64 bytes. Okay, if it's not 64 bytes long, you do some padding byte to make it at least 64. Okay, so coming to the format. For the Ethernet, of course, we say that transmission is intermittent, right? You have frame to send, you send. If nothing to send, you just stay idle. Then you have frame to send, you send. So the first issue we have to discuss is the framing. How can I know that is the beginning of the frame, and how can I know that is the end of the frame? Okay.
I was already low.
So you look at the beginning. We have the preamble, 7 bytes. It's called sync field. Okay, synchronization field. It actually is 10 10 10
Everyone just
10
gonna be
10.
like alive.
Okay, so that sender and receiver, the clock can be synchronized. Okay, so that's called bit synchronization. You know how long the bit is and where's the beginning of the bit, where's the end of the bit, right? We call it bit synchronization. Then following the 7 byte preamble, we have called as the start delimiter. Okay, that's starting frame. That starting frame actually is 10 10 10 10 1. So that is here. When you see 2 consecutive 1, then you know that is the beginning of the frame, right? That is about find the beginning of the frame. Now how can we find the end of the frame? That's here. We have this length field. Length field telling you that how many bytes we have inside the payload until the end, FCS. So that is here. The length field will help you to know where is the end of the frame. Okay, so this is
that thing just glitched
the length
hard.
field. Helping you. Okay. So that is here.
I was a Predator missile.
The
Yeah,
length
I
field
was on.
pointing to the end of the frame. So that is here. We know the beginning and then use the length field to
game is
find the end
over.
of the frame. So we know the beginning and end. Okay. So that's how we do the framing in Ethernet. Right. So now got the other fields. The destination and source MAC address. That is for each network interface card, you have one particular address we call a MAC address. It's actually bound inside the network interface card that's showing that
Why did I
who
switch
is
to
the
that?
sender,
Oh, I
who
got
is
away.
the receiver. Okay, so that's all right. Then the length field, number of bytes in information field. That is here pointing to the end, helping you to find the end of the frame, right? So, and padding, that's actually to make sure that at least the 64 bytes from the destiny address to the end, at least 64 bytes. Okay. Now last one, FCS. That is actually 4 bytes, 32 bits is polynomial coding, CCRTD 32 CRC. The purpose to do the error detection. Okay. So at the receiving side, if found the receiver frame is in error, what the Ethernet receiver will do is simply drop it, do nothing. So that is it. We simply do the error detection. If we find it's in error, we simply drop it. Okay. Of course, if it is error-free, then you will be received and then passed to upper layer. That is network layer, right? So that is. So now coming to the topology. Initially, this is the first Ethernet. is called bus topology. Okay, so we have the cable here, use the thick coax, that is here. The maximum distance, 500 meters. Okay, the data rate, 10 megabit per second. The fab say maximum distance, 5. Okay, so that is, we have the transceivers to connect the end device to the cable, right? So of course it's very difficult to work with because it's not that hard to actually bend and so on, right? Then then we change to thin coax. The distance we say change to 200 meters. Still data rate 10 megabit per second. Okay. But then another dominant topology actually is called Stomp topology. So we have the central device. Then everybody is connected to the central device. Okay. That central device can be a hub, or it can be a switch. So what you need is a hub. The hub basically is operating at the physical layer. If the hub receives a bit from one particular input port, say receive a bit from this printer, what the hub will do, the hub simply broadcast that received bit over all other ports, all other outgoing ports. So basically the hub is doing the physical layer bit broadcasting. Okay, so if it receives one bit from one port, it simply broadcasts out to all other ports. Okay, so you'll find that one feature of the hub is that
really, oh my gosh,
all the ports must operate at the same data rate because you are doing a bit level broadcasting. Okay, so all the bits should have the same interval, right? Another one is, if we say unfortunately, two users are transmitting a bit at the same time, what the hub will do? The hub will simply broadcast those two bits together to all other ports. So that means if two users are transmitting at the same time, they will collide with each other. So that is for if we are using a hub as the central device in a star topology, all the users connected to the hub belong to the same collision domain. So of course, you may ask me that, what do you mean collision domain? That means if two users belong to the same collision domain, if they transmit at the same time, they may collide with each other. However, if two users transmit at the same time, they don't collide with each other. We say those two users are belonging to different collision domains. Okay, so now coming to another device, central device, we call it a switch. Okay, if it is a switch, they are not doing the physical layer repeating. They are actually doing the switching at the data link layer. What the switch is doing, the switch receives a data frame from one input port. Then the switch will store the received data frame in a local buffer. After that, the switch will analyze the received data frame, then decide where it should be forwarded. So then you will say that actually it's store and forward mechanism. You are correct. The switch is actually doing the store and forward mechanism. You implemented the store and forward mechanism. The difference with the router is that we analyze the data, we analyze the MAC frame header. So if you look at the frame format, what information it will analyze is actually destination address. Okay, destination MAC address. Okay, so now because the switch is actually doing a store and forward mechanism, if two users belonging to different ports transmit at the same time, it is because they were stored in the local buffer and analyzed and then waiting to be forwarded. They don't necessarily to collide with each other because that transmitted bit will be stored in the local buffer. So that is here. You will see if the central device is a switch, users connected to different switch ports belong to different collision domains. They will not collide with each other. Okay, so that is. So coming to the performance of Ethernet, transmission delay and the traffic load, you will see that CSMACD, right? You will see that performance quite depends on A. What is the A? That is the normalized delay bandwidth product. Okay, that is the delay bandwidth product compared to the frame transmission time. Okay, A is actually the propagation delay T pro over X. X is the frame transmission time. Then you will find that smaller A, better performance. You will see that if we say the same over the traffic load, with smaller A, you have shorter transmission delay. Larger A, you have longer transmission delay, right? And also the achieve the throughput, that is here. You will see that for larger A, the achieve the throughput actually is smaller. Okay, so you will see for the Ethernet, the performance actually quite depends on the normalized delay bandwidth product. And the delay bandwidth product is actually the ratio of the propagation delay over frame transmission time. So for the Ethernet to have a better performance, it's important to keep your normalized delay bandwidth product small. Okay, so how to keep the normalized delay bandwidth product small? You'll find that depending on the propagation delay and frame transmission time. How to know the frame transmission time? Frame transmission time is the frame size divided by the data rate. So now, how to keep that normalized delay bandwidth product small? Even if we say we increase the data rate, then the frame transmission time is if we say we increase the data rate 10 times, then the frame transmission time will be decreased by 10. How can we keep the A normalized delay bandwidth product still small or unchanged? You have to decrease the propagation delay by 10. That means how to get the propagation delay? That's the distance divided by the propagation speed, right? Propagation speed is constant, so you have to reduce the distance. So that is, you will see that for the Ethernet, sometimes you may find that higher the data rate, shorter the distance. That is, they try to keep the normalized delay bandwidth product small. Okay, that is the reason. So you compare the Ethernet initially 10 megabit per second, and for the fast Ethernet, the data rate is 100 megabit per second is 10 times. You see the distance first dropped from 200 meters to 100 meters. Okay, so that is the first. But all other parameters remain unchanged. That minimum frame size still 64 bytes. Okay, and also we still use the CSMACD, but the dominant topology actually is star topology. Okay, so the bus topology actually is essentially abandoned, right? And if you further increase the data rate from 100 megabit per second to gigabit, that's 1,000 megabit per second. Then we say the first, this difference compared to the fast Ethernet and Ethernet is first, the minimum frame size is increased from 64 bytes to 512 bytes. Okay, it's actually 8 times increase. Okay, so that is why we have to increase that from 64 bytes to 512. That's because if you still keep the frame size minimum is 64 bytes, the transmission time is too short. The transmission time is too short for you to actually detect the collision. Or if you still want to successfully detect the collision, the distance will be too short. That will make the Ethernet almost useless. Okay, so that is the first we think that you have to increase the minimum frame size from 64 to 512. Then, of course, another consequence, if you increase the frame size, minimum frame size from 64 to 512, then you may find that if you say, I have only 32 bytes, then I have to add too many padding bytes to meet the requirement of 512 bytes, right? You may have to add too many padding. The padding basically is an overhead because you have transmitted the padding is actually useless to the receiver, right? That will make the system quite inefficient.
Wow, okay.
So another modification for the gigabit Ethernet is that we allow the bursting. That is, we allow that we allow transmit a burst, not a single data frame. What is a burst? That is a concatenation of multiple data frames put together. Okay, we allow to transmit a burst, not a single frame. Okay, so if you say I have only 32 byte frame, then you can add multiple such 32 bytes together to form a 512 byte burst. Then you transmit a burst. Okay, so that is, and also another change for the gigabit Ethernet is we only use the star topology, and the central device is switch. Okay, so each user is connected a single switch port. And remember, as I mentioned to you, if the central device is a switch, the users connect to different ports. They belong to different collision domains. They will not collide with each other. Now, if for each switch port only one user is connected to, that means the user will not collide with anyone else. So for the gigabit Ethernet, we still use CSMACD, but because the collision is impossible, so it's essentially abandoned. You don't really need CSMACD, right? If you further increase the data to 10 gigabit, again, use the star topology. The central device is switched. Then we say, because there's no collision, so officially CSMACD is actually abandoned. Okay, so that is another change of the 10 gigabit Ethernet to gigabit Ethernet is that the physical layer coding actually is also changed. Okay, it's not Manchester coding anymore. So this is the typical Ethernet deployment. You may find that many the star topology, you may have a hub, and then you have the Ethernet, and then switch, and then connect the Ethernet, right? Sometimes we may still use the hub. If you are using the hub, we say you have to, all those ports must be the same data rate. That's 10 megabit, 10 megabit, 10 megabit, 10 megabit. However, if it is switch, you don't really need to require all the ports to be the same data rate. Okay, here can be 100 megabit, okay, but here is 10 megabit. Here is 100 megabit, here can be gigabit. Because if it is switch, we use the store and forward mechanism. So it is possible you receive the data at one port at a data rate 10 megabit per second. Then when you send out, you can send it out at a data rate 100 megabit per second or gigabit. Okay, per second. So definitely you don't really need all the ports to have the data rate matched. Okay, different ports can have different data rate. So it is possible, right? So now, another issue for the Ethernet, of course, we say, remember for the Ethernet, we say we have the distance limit. Okay, if it is a hub, we say maximum 200 meters. However, if you really need a longer distance, what can we do? Right? One possibility actually is connect multiple hubs together. Okay, you use the device to connect them together. We say here is 200 meters, another 200 meters, but now if we connect them together, the distance now increased from 200 meters to 400 meters, isn't it? So the question now is how to actually interconnect those two LAN segments. You can use a hub, of course. You can use the hub to interconnect them. But one drawback of using a hub first is the data rate must be the same, and also another one is all the users belong to the same collision domain. That means for all the users at any time moment to make sure no collision, only one user allowed to transmit, right? Or you can use that. Another option is use the switch, or sometimes we call another name, called a bridge for the data link there. Use the bridge to interconnect them. It basically is a switch. So if it is a switch, we use the store and forward mechanism, right? If you use the switch to interconnect them, then all these users belong to one collision domain and these users belong to another collision domain. Okay, because we have two collision domains, then we allow at any time moment we allow in maximum 2 users to transmit at the same time. One user in this collision domain, another user in another collision domain. Okay, so you will see that. And this you will see that the performance now is doubled, right? It's possible to be doubled. Of course, you may also use the routers. Now, if it is routers, it is a network layer device, then that will belong to different networks. That's another issue, right? For us, we focus on this one, using a bridge to interconnect LAN segments. So that is here. We use the bridge, okay? Say this is Ethernet, another Ethernet, we use the bridge to interconnect that. So that is, you receive the data, then the MAC layer, then we analyze the MAC header, then you decide where it should be forwarded, then you forward out, right? If that is the bridge we are talking about, we have another LAN for such a bridge, which is called transparent bridge. What do you mean transparent? That is, the users may not even know the existence of such a bridge. To them, say in this example, we have LAN segment 1, LAN segment 2. To them, that we have 6 users. To them, they think that they all belong to the same network. They didn't even realize there's a bridge to interconnect those 2 LAN segments. It's actually like they all connect to the same cable in this particular example, right? Just like they all belong to the same cable. Okay, so now it's called a transparent. Then of course we say, what do you mean that? What do you really mean that? Okay, let me show you first the operation of the transparent bridge. In this example, right, that bridge will have 3, with receiving 1 frame. It may have 3 functions. Okay, the first function we call it forwarding. In this example, we say if user S1 send a frame to user S4, what the bridge will do? The bridge receiving that frame from user S1, then the bridge simply forward the frame to LAN segment 2 that will be received by user S4, right? It's called a forwarding. Okay, then how can you actually do the forwarding? It's actually because for the bridge, it will have a forwarding table. Okay, it will have a forwarding table which will specify that. In the example, we say the bridge will have the table, say for LAN 1, which user belongs to LAN 1, S1, S2, S3 belong to LAN 1, S4, S5, S6 belong to LAN 2. Okay, then if we find that the frame is sent from one LAN segment to another LAN segment, that is from S1 to S4, then you see if frame is sent by user in LAN 1, then it must be delivered to another user in LAN 2. What the bridge should do? Of course, the bridge will actually forward that frame from LAN 1 to LAN 2. Okay, so the key issue here is that the bridge must know which LAN segment that user belongs to. Okay, so here S1 belong to LAN 1, S2 belong to LAN 1, S3 belong to LAN 1, and S4 belong to LAN 2, S5 belong to LAN 2, S6 belong to LAN 2. Then you will find that if the sender and receiver belong to different LAN segments, then what the bridge should do, have to forward from one LAN segment to another LAN segment. That is called forwarding. Okay, another adjective we call it filtering. Is again in this example we say if S1 send a frame to S2, then the bridge receive the frame, then bridge realize that both the sender and receiver belong to the same LAN segment. Then there's no point for the bridge to forward that frame to LAN 2, isn't it? Because the receiver is not attached to LAN 2. So that is the second function for the bridge. We call it filtering. Okay. Then of course you see the key feature again is the bridge must know both S1 and S2 belong to LAN 1. They belong to the same LAN segment. Okay. Then we do the filtering. Right. So now you see if the sender and receiver belong to different LAN segments, we do the forwarding. If they belong to the same LAN segment, we do the filtering. if we say we have no idea if they belong to the same LAN segment or not, the third scenario, say S1 send a friend to S7, then the bridge will have no idea where is S7, what the bridge will do. That is the third function for the transparent bridge, flooding. Okay, so that is here we do the flooding, right? What you mean a flooding is you receive one friend from one port, you simply flood out to all other ports. Okay, in this example, because we say we have only 2 ports, so you flood out to all other ports, that's why it flood out to LAN 2. It's live in the forward, but actually if the bridge has more than 2 ports, you will find the flooding is quite different. So now you see that. Should I do the forwarding, filtering, or flooding depending on where is the source or where is the receiver, right? If so, now we have the forwarding table actually inside the bridge. Okay. So of course the next question you may ask me is how to create that forwarding table. Do we have to create and maintain a forwarding table manually, or we have one particular, say, mechanism to do that? So, say, for the transparent bridge, the beauty is that that forwarding table will actually be created automatically. So this is showing you that we have, say, scenario. Bridge 1, bridge 2, we have 3 LAN segments, right? So each bridge will maintain such a forwarding table, S2 fields, address referring to the end users, S1, S2, S3, S4, S5, and port saying that user is reachable via which port. So for each bridge here, where each port has a port number, see, in this example, we say this is port 1, this is port 2, this is port 1, port 2. Then you will see that, look at those users for bridge 1. S1 and S2 is reachable via port 1. S3, S4, S5 are reachable via port 2. Okay, and for bridge 2, that S1, S2, S3 are reachable via port 1, and S4, S5 reachable via port 2. That is the information that must be maintained in a forwarding table. Okay, so how the forwarding table is actually created, they are actually doing that automatically. Let me show you how it is done. Initially, the forwarding table is empty. Right? When the system just connected, just created, of course the forwarding table is empty. So now, let me show you how the forwarding table is created and maintained. S1 send a friend to S5. Okay, that will be received by bridge 1. Then the bridge 1 will try to decide what they should do with this incoming friend. Should I forward it? Should I filter it? Or should I flood it? Okay, so then, how can you know it should be forwarded? If the sender and receiver belongs to different ports, you do the forwarding. If the sender and receiver belong to the same port, we do the filtering, right? If the sender and receiver, you have no idea if they belong to the same port or not, we do the flooding. So that is here now, the bridge 1 received this incoming frame is sent from S1 to S5, right? So the bridge will try to check where is the sender, where is the receiver. You check the forwarding table, and then you find that we have no idea where is S1, where is S5. So we have no idea where is the sender, where is the receiver. So what the bridge 1 should do, of course, in this case, it must do the flooding because you have no idea if they belong to the same port or not, right? So it should do the flooding, but that is not the end of the story. So look at B1. You receive the friend is sent from S1. You receive the friend from port 1. That means that S1 is reachable via port 1. So that is here. After receive this friend, the bridge 1 will know something about the sender. So that is here. The sender information is actually added to bridge 1's forwarding table, saying S1 is reachable via port 1. Then bridge 1, of course, do the flooding, right? Flood that incoming friend to all other ports. In this case, all other ports are just just a port 2, right? So you flat out to LAN 2, then that will be received by bridge 2. What will bridge 2 do with the incoming frame from S1 to S5? Again, check its forwarding table. It has no idea about where is the sender, where is the receiver. Now, of course, you have no idea if they belong to the same port or not, right? Of course, bridge 2 will do the flooding, and at the same time, it will also add the source information to its forwarding table. That is S1 is reachable by port 2 because that frame is received at port 2, right? So then, flat out to upper port 2, that will be received by the destination S5, right? So let me give you another example. If now the second frame is sent, is S3 sent to S2. Okay, that will be received by bridge 1. Again, the bridge 1 will check the source and destination against its forwarding table. It has no idea where it's S3, where it's S2. So, of course, bridge 1 will do the flooding over LAN 1, right? Over port 1, that will then be flooding over LAN 1 that will be received by S2. Okay, and also at the same time, the source information will be added to its forwarding table. So that is S3 is reachable by port 2 because it actually is received at port 2. That means S3 is reachable by port 2. That is the entry regarding sender S3 is added, right? And also now look at bridge 2. It is received at port 1. That means S3 is reachable by port 1 because it has no idea where is the receiver S2. Bridge 2 will also do the flooding to all other ports that is flooded out to LAN 3. Then you will see that in this case, of course, that flooding is unnecessary, right? Because the S2 is not actually attached to LAN 3, it's actually attached to LAN 1. But to make sure the receiver will actually receive that data frame, it has to do the flooding because the bridge 2 has no idea where S2 is, right? So you will find that if we do the flooding, sometimes the flooding actually is unnecessary. Okay, the third scenario. S4 actually send a frame to S3. So that will be received by bridge 2. Okay, so the first the bridge 2 will check the information about the source S4. Then you will find that the S4 is not actually recorded in its forwarding table. So that one entry regarding S4 will be added first. That is S4 is reachable by port 2. So now look at that sender and receiver, right? Sender is reachable by port 2 and receiver is reachable by port 1. They belong to different ports. So what the B2 should do, it should do the forwarding. That is forward the incoming frame to output port 1 because receiver is reachable by port 1. That is forward to port 1. Okay. So if it is forwarded to port 1, that will also be received by bridge 1. Okay. Then the bridge 1 first, check the source information. Then you will find that S4 is reachable by port 2. Next, bridge 1 will check the reachability of both the sender and receiver. Then you find that both are reachable by the same port, port 2. Okay, that means the bridge 1 should do the filtering. That is simply do nothing. We drop the incoming frame, right? Okay, that is where we should do the filtering. Okay, another scenario. Okay, one more frame sent from S2 to S1. Okay, so that is here. That will be received by bridge 1. First, check the sender. S2 is sent by sender S2. It's reachable. It's received by port 1. That means S2 is reachable by port 1. Then you check the destination S1. S1 is also reachable by port 1. They both are reachable by the same port. So B1 will simply do the filtering. That is do nothing. Okay, so that is here showing you. Okay, then of course that forwarding table, you'll find that because one feature of that LAN is that the user may move from one LAN segment to another LAN segment, then move to the third LAN segment and so on, right? So For example, here we say S2 initially is attached to LAN 1. If it moves to LAN 2, then S2 regarding the B1, it will be reachable via port 2. So that means this entry regarding S2 is outdated. Okay, have to be delayed and be modified from port 1 to port 2. So that is here. Such a movement can be actually updated by the forwarding table. Is we use the adaptive learning. Okay, so that is here first. For each entry, it has a time limit. Okay, say it will only last 10 minutes. After 10 minutes, it will, if the S2 is not sending frame anymore, such an entry will be delayed. And second, if S2 is moved to LAN 2, then you send a frame, then it will be received by bridge 1 by port 2, then this entry will be changed from port 1 to port 2. Okay, it's called.
Has to be the last match. That's 3 of them, man. Should have been shooting while I was going back.
Adaptive learning. But so that finished our lecture on the data link layer. Next, we move to another topic. That is network layer. Okay, so we will actually spend 2 weeks on the network layer. So now what is network layer doing? So this is the first. What the network layer do? What the network layer actually doing is that network layer is move the information block from the sender to the receiver via a sequence of networks. That is what the network layer is doing. Say, for example, here we have a laptop that connect to that belong to this network. Okay, it wants to send a send some information to this server. Okay, what the network layer is doing is network layer will move the information from the sender via a sequence of networks to the receiving side. That's this server. So that basically what the network layer is move the data from source to destination device. Okay, so that is here. So for us to do that, 2 functions we need to do. First is from source to destination, we need to find such a physical path. So that is the first function of the network layer. Find the physical path. We have another name for that. We call it routing. Okay, we have to do the routing to find the physical path from source to destination. And the second function for the network layer is after such a physical path is found, it's already there. We need to move the data from source to destination. That is the second function of the network layer. We call it forwarding. Okay, that is actually physically move the data from source to destination, right? The routing is to find such a physical path, and second, forwarding is to move the data over such a physical path from source to destination. Okay, so the network layer have to be implemented inside the network. Okay, so that is here the data actually sent and so on, eventually coming to the destination. Okay, so that is 2 key functions of the network layer. One is routing, determine the route taken by packet from source to destination. And second function is forwarding, move the packets from the router's input to appropriate output. Okay, so that is here. How those two network layer functions are actually implemented. The first, look at the network device, say this router. You receive a data frame. Okay, then you have to move the data frame from the input port to one of those output ports. Okay, so the first you have to determine which output port this incoming data must be forwarded to, should be used to do the forwarding. Okay, so that is, which say you have output port 1, output port 2, output port 3. Here we say you have to move to output port 2. Why? Output port 2. So that is here. We say for each router, we maintain a routing table. Okay, inside the routing table, it will specify which output port should be used to forward this particular incoming data. Okay, we call the packet. Okay, where to forward this incoming packet, right? So that is the routing table. Okay, each router must maintain its own routing table. That routing table will decide for one particular incoming packet which output port should be used to forward this incoming packet. Okay, so now of course you may ask me that, hey, how this routing table is created and maintained? That is the routing algorithm. Okay, I will show you in more details later how the routing algorithm is actually implemented. What routing algorithm can we use? How it is implemented, right? So now let's assume we do have this routing table. Then how can you know which output port should be used? So that is what's inside this routing table.